Hello student, in today's session we are going to discuss about p block elements. We will discuss certain properties of p block elements along with the inert pair effect. So first question is, what do you mean by p block elements? So the elements in which the last electron enters in any one of the three p orbital. We have in p subcell three orbitals px, py and pz. So the last electron enters in any one of the three p orbital of their outermost cell. So as you know that the number of p orbital is 3. Thus the maximum number of electron that can be accommodated in a set of p orbital is 6. Consequently, there are 6 groups of p block elements in the periodic table numbering from 13 to 18. So p block elements we have 6 groups starting from 13 and the last one is 18. Except for helium, the valence shell electronic configuration of p block element is ns2 np126. And we know that the maximum or group oxidation state shown by the p block element is equal to the total number of valence electrons, that is sum of s and p electrons. So one can write that the maximum oxidation state that can be shown by the p block element is equal to the sum of the s electrons and p electrons. Now if you see group 13 elements, that is boron family. Boron is the head of the family. So in boron basically we have the two types of isotope. One is 5b10, another is 5b11. The percentage abundance of 5b10 is 19%, very low, and the percentage abundance in the earth crust, that is 81% of 5b11. So boron mainly occurs in the following forms: orthoboric acid H3BO3, or one can write BOH whole thrice, borax Na2B4O7.10H2O, and kernite KNa2B4O7.4H2O. So if we write the electronic configuration for 13 group element, one can write the general electronic configuration is noble gas NS2 NP1, and here the value of N that goes from 2 to 7. Here we have elements for the group 13: boron, aluminium, gallium, indium, thallium and nihonium. Boron is B, aluminium is Al, gallium is Ga, indium is In, thallium is Tl, and nihonium is NH. And here these are the atomic number: boron 5, aluminium 13, gallium 31, indium 49, thallium 81, nihonium 113. And here this is the nearest noble gas configuration for boron: helium NS2 NP1, for aluminium neon 3s2 3p1, for gallium argon 3d10 4s2 4p1, for indium krypton 4d10 5s2 5p1, for thallium xenon 4f14 5d10 6s2 and 6p1, and for nihonium you will see that Rn 5f14 6d10 7s2 and 7p1. So here the general electronic configuration, you can see the nearest noble gas configuration, then ns2 np1. Here you will see 2s2. As you move downward, you will see the principal quantum number is going to increase here. So that's why here n is equal to 2 to 7 for the boron family members. This is the electronic configuration. Here you can see that the existence of d orbitals in case of gallium and indium, and the existence of f and d orbitals are there in case of thallium and nihonium. Further, if you see that the boron and aluminium have the noble gas core, you can see boron and aluminium has the noble gas core. Gallium and indium have noble gas plus 10d electron core, noble gas plus 10d electron cores in case of gallium and indium. and thallium has noble gas plus 14F, thallium and nihonium, 14F and plus 10d electrons are there in the core. Now if you look over the atomic and ionic radii, group 13 elements have lower atomic and ionic radii in comparison to the group 2 elements. As we move from left to right, means in a period from the group 2 to group 13, atomic number increases, due to which the nuclear charge increases and size decreases. We have the relationship that atomic radii is inversely proportional to nuclear charge. Higher is the nuclear charge, lower will be the value of, or you can say atomic radii will be lower. And we know down the group, atomic or ionic radii increases due to increase in the number of cell. But as we move from group 2 to group 13, the atomic or ionic size keep on decreases because effective nuclear charge that will have the higher value. So if you see, in case of aluminium and gallium, aluminium is 13, gallium is 31, electronic configuration, neon 3s2, 3p1 for aluminium, argon 3d10, 4s2, 4p1 for gallium. Atomic radii, when radius value is given in picometer, for aluminium it is 143 and for gallium it is 135. You will see that the value of atomic radii for gallium is lower and for aluminium is higher. Why it is so? The reason behind this is because if you see the electronic configuration, in case of gallium you will see the 3d electrons are there. Here there is no existence of d orbital, but in case of here you will see 3d orbitals are there, 10 electrons are there in the d orbital, so they offers poor screening or shielding effect for the outer electrons from the increased nuclear charge in gallium. And just because of that, what you will see that as a result, electrons in the gallium experience greater force of attraction by the nuclear than in aluminium, because there is no poor shielding of the there is no d orbital, means there is no poor shielding. S and P have the strong shielding effect, and here due to the presence of the d orbital there is poor shielding effect, due to which the effective nuclear charge will be high. That's why the gallium will have the lower value of atomic radius in picometer in comparison to aluminium. You will see that the order of atomic radii is given here. Boron will have least value and thallium will have the highest value. Boron will have 85 picometer. Gallium will have lower value than that of aluminium. Reason being, in gallium poor shielding of the d orbitals. D orbital electrons are there. That's why here the size is reduced. It is 135 picometer. In case of aluminium it is 143 picometer, and indium 167 picometer, and thallium it is the largest one, 170 picometer. So this is the order of atomic and ionic radii for the group 13 element, that is boron family. Now if you see the ionization enthalpy, the value of ionization enthalpy for the first ionization enthalpy for group 2 is greater than that of the first ionization enthalpy for group 13. Despite of the smaller size of group 13, it will have the lower value of ionization enthalpy, because we know that in a group 13 element the last electron has to be removed from the p orbital, and in group 2 the last electron has to be removed from the s orbital, and we know that the electron removal is quite easier in case of p orbital than in s orbital. That's why here in case of group 13 the first ionization enthalpy will be lower than that of group 2 first ionization enthalpy. So first ionization enthalpy of group 13 element, that is delta IH1 in kilojoule per mole. We have the order. Boron is highest and indium is the you will see the lowest value. So order will be B, then TL, then Ga, then Al, and the indium will have the least value. Ionization enthalpy of thallium is greater than indium due to the inability of D and F electrons, which have the low shielding or screening effect to compensate the increase in the nuclear charge. That's why you will see in the case of thallium, in case of indium, here in indium only d orbital electrons are there, but in case of thallium along with the d we have the 5 orbital electrons are there. And we know that d and f both have the very poor shielding effect. That's why the value is value of ionization enthalpy for aluminium is low. Aluminium is higher in comparison to boron, and indium is greater ionization enthalpy than that of gallium, because ionization enthalpy is inversely proportional to size. As the ionization enthalpy decreases, the size will increases. And general trend for the ionization enthalpy of group 13, we will have this boron will have higher value in comparison to aluminium, and this thallium will have higher value of ionization enthalpy in comparison to indium, and the gallium will have higher value for aluminium as well as for indium. So this is the order of ionization enthalpy for group 13. Now if you see that in group 13 elements, ionization enthalpy is directly proportional to the effective nuclear charge. So here you will see the successive ionization enthalpy means removal of electrons from the 13 group element, that is very difficult, right? So here you will see the order of the ionization enthalpy. Third ionization enthalpy will have the highest value in comparison to second and first. So one can write ionization enthalpy is directly proportional to effective nuclear charge. Now if you look over the electronegativity, as you know that down the group value of electronegativity decreases. So boron will have the highest value of electronegativity 2.0, and thallium will have the least value 1.8. Electronegativity marginally increases down the group. Our general trend is down the group electronegativity is going to decrease, but here electronegativity in case of group 13 element, that is marginally increased down the group from aluminium to thallium due to the increase in the effective nuclear charge. As a result, force of attraction of the nucleus for the electron increases. That's why you will see that the value of electronegativity as we move, that will increase, but the increase is not very much significant. So the electronegativity order for the group 13 is boron will have the highest value of electronegativity, and thereafter thallium, then indium, gallium and aluminium will have the least value of electronegativity, right? So greater the value of greater the electronegativity of group 13 element, lesser is the ionic character of the trihalides. So the electronegativity value in case of group 13 is boron is greater and aluminium is least. So likewise here the ionic character will be higher in case of AlCl3, because greater the value of electronegativity, lesser will be the ionic character in their trihalides. Now if we look over the boron is non-metallic in nature. Boron is extremely hard and black colored solid. It has usually high melting point 2453 Kelvin, lowest density 2.35 gram per centimeter cube at 298 Kelvin amongst group 13 elements. Now question is why the boron has the highest melting point? Because it has because boron in its B12 form, it exists in the icosahedral structure. That's why the unusually high melting point has been observed in case of boron. So boiling point, if we look over the boiling point and melting point, as you know, down the group the boiling point decreases from boron to thallium due to decrease in the metallic bonding with increase in size. So order of boiling point will be boron will have the highest value and thallium will have the least value. And if you look over the melting point decreases from boron to gallium and then increases from gallium to thallium. So here this is the order of what melting point. Boron will have the higher value for boiling as well as for melting point, but there is change in the order of melting and boiling point. Here you will see melting point decreases from boron to gallium, then increases from gallium to thallium. So this is because of the because aluminium, indium and thallium, they have the closed pack structure. So closed pack structure will have the higher value of melting point. Now next moving to the inert pair effect. Inert pair effect, or another name for this is inert S pair effect. This is the reluctance or unwillingness of the S electron to participate in bond formation, right? And or you can say that is the non-participation of Ns or outer S electron in the bond formation, and this is just because of the intervening of D and F orbital because of their poor shielding effect, right? So this is inert pair effect. We will understand it just by taking examples. Here aluminium is there, 1s2, 2s2, 2p6, 3s2 and 3p1. Now if we remove one electron from this p orbital, so here as we know that it can lose one electron to form oxidation state 1. It is lower oxidation state. Here the loss of electron will take place or not, that will depends upon the immediate subcell. So here this is the immediate subcell to this p orbital. So the loss of electron will take place or not, that will depends upon the immediate subcell. Here this is S. So here aluminium is going to send its nuclear charge. Here we know that S orbital have the highest screening effect. Due to this it will prevent the nuclear charge. It will prevent the nuclear charge of attraction to the large extent. That's why this electron will be easily removed. So aluminium can show lower oxidation state +1, but if we further if you want to remove the electron from the S orbital, then that depends upon the next immediate cell, that is 2p. And as we know that the p orbital again have a high, or you can say greater value of screening effect. That's why it will be it can be easily removed. These two electron can be easily removed. So maximum oxidation state that can be shown by aluminium is +3. So because S and P orbital will have the higher value of screening effect, that's why they are going to reduce the effective nuclear charge to the maximum extent here. So here S electron that will be easily removed because they are feeling less nuclear effect, so they can be easily removed. Again if we see gallium 31, electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2 and 4p1. So here Ga+1 means after loss of one electron, and the loss that depends upon the next immediate cell, the nature of the immediate cell, because we know that S orbital will have the higher screening effect, so it will reduce the effective nuclear charge to a maximum extent, so that this p electron can be easily removed. So gallium will exist in +1 oxidation state, in the lower oxidation state. Now further if we want to remove the S2 electron from the S orbital, then we know that depends upon the next immediate cell, that is D, and D has the poor shielding effect. Just of the poor shielding effect of the D orbital, what it will do, that this the effective nuclear charge will be so high that it cannot be you can say it cannot be prevented by this d orbital, so it will be gained by these two electrons. So non-participation means these two electrons, they will be more attractive towards the nucleus, because this d orbital, poor shielding of d orbital, they are not going to stop the effective nuclear charge. That's why these two electrons, they will remain paired. so they are not going to form the bond. So not participate in these 2 electron of s orbital. They are not participate in bond formation because they will remain inert, and so this pair will remain inert. So this is called inert pair effect. So we have the question for this, and question is, how can you explain higher stability of BCl3 as compared to TlCl3? We have boron and this thallium. Electronic configuration for boron is 2s2 2p1. For thallium, xenon 4p 4f14 5d10 6s2 6p1. So electron participate in bond formation. We can say 2 from the S and 1 from the P. Total we have the 3. So stable oxidation state is +3, and stable chloride, it can bind up 3 chlorine atoms, so it will form boron trichloride. Likewise in case of xenon, here only 1 electron of 6p orbital participate in bond formation because this pair will remain inert. So this is not going to participate in bond formation. So only 1 electron or only 6p electron participate in bond formation. So 2,6s2, these electrons, they will remain inert. So stable oxidation state for thallium is +1, so it can bind with the 1 chlorine, so it will stable chloride for this is TlCl. Higher stability of BCl3 as compared to TlCl3 is due to the inert pair effect in case of thallium chloride. So thallium is more stable in +1 oxidation state because it has the highest value of inert pair effect. That's why it can lose only 1 electron. So stable oxidation state for thallium is +1 and for boron is +3. So thank you so much for watching this video. Have a great day.